In a previous video, I claimed to have condensed liquid oxygen out of the air using the apparatus you see here. I poured liquid nitrogen into an aluminum pan, and drips immediately started to fall into a cup placed below the pan. Because the pan was cooled to below the condensation point of oxygen, which is 90 Kelvin, I assumed that the drips were comprised of liquid oxygen. However, upon further experimentation, I now believe these droplets to be formed from liquid air and not from pure oxygen. In this video, I'll share with you some of the experiments I've done to lead me to this conclusion. I first decided to collect some pure liquid oxygen to get an idea of how it behaved. To do so, I first connected this condenser coil to the outlet hose of a tank of oxygen. Next, I cooled the condenser coil in some liquid nitrogen. I then got a cup to collect the liquid oxygen in, placed it beneath the outlet to the condenser coil, and turned on the flow of the oxygen. The oxygen flowed through the condenser coil, and while doing so it was cooled to below its condensation point. Thus, liquid oxygen flowed out the end of the condenser coil. Here's a close-up view of liquid oxygen exiting the condenser coil. Next, I collected some liquid air. Just like I did in a previous video, I poured some liquid nitrogen into an aluminum pan placed above a styrofoam cup. The pan was cooled to below the condensation point of air, which is 79 Kelvin. When air struck the pan, it condensed, forming a liquid that dropped and was collected in the cup. Next, I decided to compare the properties of the liquid air and the liquid oxygen collected. In the cups you see here, liquid nitrogen is on the left, liquid air is in the middle, and liquid oxygen is on the right. Look carefully at the colors of these three liquids. We see that liquid nitrogen is colorless, liquid air, which is in the middle, is a very faint blue, and liquid oxygen, which is on the right, is blue. If we recall that air is made of 78% nitrogen and 21% oxygen, then the very faint blue color of the liquid air in the middle makes sense. Let's go ahead and test the magnetic properties of these three liquids. A strong magnet placed in nitrogen shows that nitrogen is not attracted to a strong magnet. A strong magnet placed in air shows some attraction. That would be the oxygen in the air that's being attracted to the strong magnet, leaving the nitrogen behind in the cup. And then we'll go ahead and test the liquid oxygen, and of course the liquid oxygen is attracted to the strong magnet. Now we'll test the ability of these three liquids to support combustion. We'll start with liquid nitrogen first. I'll take this paper towel and soak it with some liquid nitrogen, and then I'll try to light it on fire. It looks like the nitrogen evaporating from the paper towel is putting out the flame from the lighter. Nope, it looks like nitrogen does not support combustion. Now we'll try the same thing with liquid air. I'll take my paper towel and pour some of the liquid air on top, and then we'll try to light this with a lighter. Wow, those are some big pops. Yeah, it looks like air is supporting combustion. Of course it does. There's a lot of oxygen concentrated into that paper towel from the air. Alright, now let's try oxygen. Look at that beautiful blue color of the oxygen. I just love that blue color. Okay, we'll pour it into the paper towel and then try to light this on fire. Wow, those pops are really loud. Get this lit here. Yep, oxygen supports combustion. Now we'll use a thermocouple to test the purity of each liquid. Here the thermocouple is placed in some liquid nitrogen, which is boiling, and we see that the temperature recorded is right around 77 Kelvin. Given that the literature value for the boiling point of nitrogen is 77.2 Kelvin, we can be reasonably confident that our sample of nitrogen is quite pure. Now we're going to test the liquid oxygen. We'll put the thermocouple in the liquid oxygen, and we see that the boiling temperature is hovering right around 90.5, 90.6 Kelvin. And given that the boiling point of oxygen is 90.2 Kelvin, once again we see we have a fairly pure sample. Now we're going to test the boiling point of the air we collected from condensation off of a cooled aluminum pan. The boiling point of air is 79 Kelvin. And as we can see, the boiling temperature of our mixture collected is higher than that. We also notice as time goes on, the boiling temperature of the fluid in the cup tends to rise. Here's what I think's going on. I think that the air collected from condensation off of the aluminum pan is rich in oxygen, meaning it has more than 21% oxygen in it. That's going to make its boiling temperature a little higher than 79 Kelvin, which is the literature value for the boiling point of air. I also think that as the air boils, it is the nitrogen in the air that tends to boil away, leaving behind oxygen. I think this because you'll notice that over time, the boiling point rises and tends towards the boiling point of oxygen, which is 90.2 Kelvin. Let's watch this happen. Yep, right around here we've got pretty much pure oxygen. In conclusion, I believe when an aluminum pan is filled with liquid nitrogen and liquid condenses off of that aluminum pan, the liquid that condenses off the aluminum pan is oxygen-rich air.